Slew Rate. Op-amps used in feedback circuits exhibit large signal behavior called skewing. We first describe an interesting property of linear systems that vanishes during skewing. Consider the simple RC network shown in figure, where the input is an ideal voltage step of high V0. Since V out is equals to V0, 1 minus exponential of minus t by tau, where tau equal to RC, we have d of V out by dt is equals to V out by tau exponential minus t by tau. Here you can see the response of a linear circuit to response of a linear circuit to input step. Figure a response of linear op-amp to step response, that is, the slope of step response is proportional to the final value of the op-amp. If we apply a larger input step, the output rises more rapidly. This is a fundamental property of linear systems. If the input amplitude is say doubled while other amplifiers remain constant, the output signal level must double at every point, leading to a twofold increase in the slope. The foregoing observation applies to linear feedback systems as well, shown in figure. In an example where the op-amp is assumed linear, here we can write V in minus V out R2 by R1 plus R2A minus V out 1 by R out is equals to V out by R1 plus R2 plus V out CLS. Assuming R1 plus R2 very much greater than R out, we have V out by V in of S similar to A by 1 plus A R2 by R1 plus R2 into R1 plus R out CL by 1 plus A R2 by R1 plus R2 as expected. The both frequency as expected to the low frequency gain and the time constant are divided by 1 plus AR2 by R1 plus R2. The step response is therefore given by V out equal to V0 A by 1 plus AR2 by R1 plus R2 into 1 minus example minus T by CLR out by 1 plus AR2 by R1 plus R2 U of T, indicating that the slope is proportional to the final value. This type of response is called linear settling. With a realistic op-amp, on the other hand, the step response of the circuit begins to deviate from equation as the input amplitude increases, illustrated in figure. The response to sufficiently small inputs follows exponential of equation, but with large input steps, the output displays a linear ramp having a constant slope. Under this condition, we say the op-amp experiences skewing and call the slope of the ramp the slew rate. To understand the origin of skewing, let us replace the op-amp of figure by a simple CMOS implementation figure, assuming for simplicity that R1 plus R2 is quite large. We first examine the circuit with a small input step if V in experiences a change of delta V, ID1 increases by gm delta V by 2 and ID2 decreases by gm delta V by 2. Since the mirror action of M3 here you can see in this figure skewing in an op-amp circuit, small signal operation of a simple op-amp, and M4 rises mod ID4 by GM delta V by 2. The total small signal current provided by the op-amp equals GM delta V. This current begins to change CL, but as V out rises, so does Vx, reducing the difference between Vg1 and Vg2, and hence the output current of the op-amp. As a result, V out varies according to equation. Now suppose delta V is so large that M1 absorbs all of SS turning of M2. The circuit then reduces to that shown in figure, just generating a ramp output with a slope equal to SS by CL. If the channel length modulation of M4 and the current drawn by R1 plus R2 are neglected, note that so long as M2 remains off, the feedback loop is broken and the current charging CL is constant and independent of the input level. As V out rises, Vx eventually approaches V in, M2 turns on, and the circuit returns to linear operation. In figure, skewing occurs for falling edges at the input as well. If the input drops so much that M1 turns off and the circuit is simplified as in figure, discharging CL by current approximately equal to SS. After V out decreases sufficiently, the difference between Vx and V in is small enough to allow M1 to turn on, leading to linear behavior thereafter. Here you can see in this figure skewing during low to high transition. In this figure, skewing during high to low transition. The foregoing observations explain why skewing is a nonlinear phenomenon. If the input amplitude say doubles, the output level does not double at all points, because the ramp exhibits a slope independent of the point of the input. Skewing is an undesirable effect in high-speed circuits that process large signals, while the small signal bandwidth of a circuit may suggest a fast time domain response. The large signal speed may be limited by the slew rate simply because the current available to charge and discharge the dominant capacitor in the circuit is small. However, since the input-output relationship during skewing is nonlinear, the output of a skewing amplifier exhibits substantial distortion. For example, if a circuit is to amplify a sinusoid V0 sin omega naught t in the steady state, then its slew rate must exceed V0 omega naught. As another example, let us find the slew rate of the telescopic op-amp shown in figure A. When a large differential output is applied, M1 or M2 turns off, reducing the circuit to that shown in figure B. Thus, V out and V out appear, V out 1 and V out 2 appear as ramps with slopes equal to plus minus ISS by 2 CL and subsequently V out 1 minus V out 2 exhibit a skew rate equal to ISS by CL. Of course, the circuit is usually used in closed loop form. It is also instructive to study skewing behavior of a folded cascade op-amp with single-ended output. Figures A and B depict the equivalent circuit for. Here you can see in this figure skewing in telescopic op-amp. In this figure you can see skewing in folded cascade op-amp. Positive and negative input steps respectively. Here the PMOS current sources provide a current of IP and the current that charges and discharges CL is equals to ISS, yielding a skew rate of ISS by CL. Note that the skew rate is independent of IP. If IP is less than or is greater than or equal to ISS, in practice we choose IP similar to ISS. In figure A, if ISS greater than IP and during skewing M3 turns off and Vx falls to a low level such that M1 and the tail current source enter the triode region, thus for the circuit to return to equilibrium after M2 turns on, Vx must experience a large swing slowing down the settling. This phenomenon is illustrated in figure. To alleviate this issue, two clamp transistors can be added as shown in figure A. The idea is that the difference between ISS and IP shown now flows through M11 and M2, requiring only enough to drop in Vx and Vy to turn on one of these transistors. Figure B illustrates a more aggressive approach where M11 and M12 clamp two nodes directly to VDD. Hence figure long settling due to the overdrive recovery after skewing. Clamp circuit to limit swings at S and Y. The equilibrium value of X and Y is usually higher than VDD minus VTH, and M11 and M12 are off during small signal operation. What trade-off are encountered in increasing the skew rate? In the examples of figures for a given load, capacitance ISS must be increased, and to maintain the same maximum output swing, all of the transistors must be made proportionally wider. As a result, the output dissipation and the input capacitance are increased. Note that if the device currents and the width scale together, GM_R0 of each transistor, and hence the open loop gain of the op-amp remain constant. How does an op-amp leave the skewing regime to enter the linear setting regime? Since the output, hence the point at which one of the input transistors turn on is ambiguous, and the distinction between skewing and linear setting is somewhat arbitrary. The following example illustrates the point. In the above example, the value of alpha determines the onset of linear setting. Depends among other things on the actual required linearity. In other words, for a linearity of 1%, alpha can be quite larger than for a non-linearity of 0.1%. The skewing behavior of two-stage op-amps is somewhat different from that of the circuit studied above. This case is studied in chapter. Thank you.